see?
Yes, okay. The first presentation is exploring the limits of an RBSC-based approach in solving the subset selection problem. Okay, please start.
Okay, today my name is Parisa Supitayakul from Okayama University. Today I would like to present exploring the limit of an RBSC-based approach in solving the subset selection problem. So, like most of the real-life process involve the certain degree of the randomness. So the observation obtained from some process are treated as a random variable and represent in terms of stochastic model. So the conventional research problem of ranking and selection in here we call INS of the research field of computational statistics focus on such process involve the random factor. So specifically, INS problem is the problem of choosing the best of two processes, which bear certain degree of randomness according to a given performance measure. So in solving the INS problem due to the stochastic nature of the system, it is desirable to take as many measurements as possible and increase the reliability of decision. So this implies that numerous physical experiment needs to be carried out. But however, in certain cases, it may not possible to make the physical experiment, for example, like a traffic safety analysis, because like it's a little bit dangerous for the human to do some like safety analysis by themselves. So in some like pharmacological study, like physical experiment might cost a long time and financial resort. So in that respect, simulation is considered to be a suitable tool for the exploration of process performance. But however, since like stochastic model of the system in focus are like often highly complex, the simulation may cost like significant time and computational resort. So an S algorithm try to find a good solution in a sufficient way, namely like without an excessive number of the simulation. So in the past, as problems are like often formulated in the agriculture and clinical scenario, but recently has extended to the traffic safety or digital product selection. So while most INS algorithm aims shooting the single best process, certain others serve for a subset of process. So it's called subset selection problem. So about the subset selection problem, it may have various purposes, like for example, first, reinforcement agent measurement noise. So if the measurement contains a noise, the solution chosen as a single best process may not be the true best solution. So then we need to choose a subset of the solution and then study them deeper. And for another example is like a post hoc analysis. The second step algorithm or follow-up simulation of the subsequent process can be tested in conjunction with a subset of solution to achieve more accurate and realistic results. So here I would like to give an example of application of subset selection problem. So for instance, McDonald's aimed at identifying the safety measure which can improve the traffic safety. So when we talk about the traffic safety, so traffic accident may have like various factors like misplanning, poor maintenance, or some insufficient driver knowledge or some weather condition. So if one considers a certain administrative regions like a city or state with a highest rate of traffic fatality, he or she address the condition of that region, but may overlook other factors related to other regions. So, however, by formulating the problem as an S problem, the larger variety of contributing factors can be identified, and moreover, by considering it as a subset selecting problem, the least favorable configuration can be detected by contrasting the worst population to the best population. So by this way, the impact of the relevant factor can be magnified. So let's go into our research. So in this study, we focus on the subset selection problem and offer adapting the RBSC-based deck generation algorithm, RBSC subten, to solve it. So first, we are using a variety of hypothetical datasets by changing an underlying distribution and the number of the samples. With the under diverse constraints like relaxing and typing the DSIR specification of the selected subset. So for each combination, we assess the feasibility of the problem, rate of saturation, and accuracy of the obtained solution. So first, I would like to give an overview of the algorithm RBSC subten. So this algorithm builds a DSIR number of subsets out of a large set of which satisfy a DSIR ranking relation. To that end, it employs rank by serial correlation, or we can call RBSC coefficients law. So the law value defines a correlation relating a dichotomous variable and the ranking variable. And this RBSC coefficient is calculated based on the simple difference formula of Kirby. So next, I will give a short explanation for the simple difference formula. So let's consider two track and field teams, Team A and Team B, and following hypothesis that Team A is faster than Team B. So the first variable is for the question, Team A is faster than Team B. So the answer of this question, it should be like yes or no, true or false. So this answer, true or false, can be considered as a dichotomous variable. It's like a two category that distinct. And the next variable is the time it takes the athlete to run to the track. So this one is also can transform into the ranking variable. So to evaluate the validity of the hypothesis, the running time of each pair of athletes from the two different teams are compared. So here is a simple difference formula. So we use a number of supporting evidence and number of contradicting evidence as S and C to compute the RBSC coefficients alone. By using this formula, we can get the RBSC coefficients. So this one can give an idea of to calculate the RBSC coefficient. Then we can use this coefficient in the algorithm. So here is the outline of the RBSC subten. So as I tell, we calculate the RBSC coefficient is in the middle. So we have the universal set and potential subset here. So the algorithm is that we get some item from the universal set to build up two potential subsets. And then we calculate the RBSC coefficient of that potential subset. If the RBSC coefficient is reached to the quantifier that we have set it, we can stop to create the potential subset. We can stop to create the subset and we can get the output. But if not, we can go to the universal set, get the new one, get the new item, add it into the subset, and then update it. After that, we can compute the RBSC again until it's reached to the deserted RBSC coefficients, or we can call low star. So here is like a pseudocode for the algorithm that I have said. We build the potential, we have the limit 1, compute the RBSC coefficients, and then check the condition. If it leads to the deserted RBSC coefficients, so we just stop. But if not, we just go update again and again until we get the output. So I would like to explain for the hyperparameter of RBSC subten. So here we have 4 hyperparameter. First is the DSIR value of RBSC coefficients, or we call low star. So this one is can called to be like a margin between the subset. So as low star is increased, there will be a larger margin between the score of the item in the subset. And for the second one is the size of the universal set. We call this one is L. So if the universal set is large, the algorithm is expected to have sufficient freedom in choosing the score and to be likely to convert easily. And the third one is the maximum permissible. The disparity on row star is can call it epsilon. So it is not always be possible to achieve the exact value of the low star. So it is necessary to define an error margin. So like if the value is go into this margin, we can say like it is acceptable. And the last one is the size of the target subset. So in here we call S. So an increase on S has a limiting effect on the freedom of choosing the score. So it can also make the effect of individual score less significant in iterative update. So here is a set of hyperparameters that we use for tests. So RBSC substance is tested with each pair of hyperparameters given in this table. So for example, when we test the value of low star with the epsilon, so we will set the L and S to be the default value, and we have like many pairs, so we just like serve it together. To assessing the performance of rate of saturation, number of iterations until convergence, and the last is disparity on these RBSC coefficients, delta P. So next, let's go to the result of rate of saturation. So from this figure, we can see like the dark blue region and the yellow area. So the yellow area is, let's say, to be like have a high rate of saturation. So first, the hyperparameter pair P low star and S pose a more serious challenge. If both low star and S are large, then there is a risk that the algorithm gets saturated, and the large value of low star pose a risk of saturation also when they are covered with a small value of epsilon and small value of L. So in here is figure B, D, and F. So we can see like the figure F have a very big space for the yellow part. So this one is a figure for low star and S, and the B is low star and L, and D is low star and epsilon. So next, when the large value of S are covered with the small value of epsilon or small value of L, a list of saturation also emerges. So here we can see in figure C and E, they have some yellow part in the corner of the figure. So when comparing the epsilon and L, the list is seems to be like more serious for epsilon than L. So that is the figure E, we have a big part of the yellow more than the C figure. As the pair of epsilon and L, the risk of saturation is not serious, and the algorithm is likely to yield a satisfactory outcome. So here we can see like in the figure A, there are no like yellow part here, so it is said to be like they are not serious. Then we go to the result of relating the number of iterations. So in the figure 3, the dark blue region signify either like the problem is not feasible or run are found to be saturated. So if it's the first case, there's no solution. But if for the second case, we can try to improve the algorithm. So let's see into the figure A, B, and C. So this one is involve an infeasibility, so that is no solution there. But for figure E and F involve some constant saturation, so this one we can improve. So focus on the successful execution. We see that after low star and S has a larger number of saturation, a higher number of iterations are required to solve most problem relating to epsilon and S. Also, the number of iterations are high for most epsilon and S and epsilon and low star pair. Although saturation is not as common as low star and S. So for the last result that we have is the disparity on this RBSC delta P. So as long as like epsilon is one of the hyperparameter under investigation, so delta P is depend solely on it. So we can see like in figure A, D, and E, the yellow part is always in the top of the figure, and the blue is going to the like in the bottom. So that is because delta P is depend on that one. And the other hyperparameter under investigating does not introduce a prominent effect on the length of saturation or the number of iterations necessary to find a solution. So this is not surprising, like because the termination of iteration is decided based on the epsilon value in the algorithm. So this study focused on a subset selection problem and apply RBSC subject on it, whose objectives share many common aspects with the generic subset selection problem. Namely, RBSC subject is originally designed for automatically build a desired number of vocabulary text out of a large corpus with a desired level of word frequency relation. So RBSC subject is due to generate subset out of universal set coming from the different underlying distribution and different size. Imposing very constraint on the subset size, ranking relation and permissible disparity, the efficiency of the RBSC subject is investigated. So the result is indicate that RBSC subject can be used in subset selection provided that it is formulated as a ranking relation, and RBSC subject is found to be sensitive to a first subset size S followed by the deserted RBSC coefficient low star, and next is permissible disparity or epsilon, and finally the universal set L. The figures present in this study are for output value coming from the standard normal distribution. So we examined the result concerning other distribution and did not observe any significant difference. Okay, so thank you for your attention.